Hi everyone, and welcome back to another one of these videos. So as you can see in this video, we're going to be talking about simple pulleys, and consequently the next video also. But for this video, I just want to talk about tension and going around pulleys, and nothing too crazy in this video. Next video gets a little bit worse, but that's physics and engineering for you. It always just gets worse. Never gets better. But as long as you truck through them, you get better and better and better. So I don't mean to freak you out with that statement, but it is true. Your life does not get easier. As you learn more, it gets more complex, which is, how things work. So anyways, so as you saw in my tension videos, you saw that the tension in one part of a rope is going to be the same as the tension in another part of the rope. And that's if you consider the rope massless. So what if you go around a pulley though? Is it going to be the same scenario? So it is going to be the same scenario, and that is if the pulley is massless, or considered as massless, basically negligible from the whole system. But so in the end, then you're going to get a T right here and a T right here also. So it's going to be like the same scenario right here, but I'm going to prove it for you real quick. So this is going to be T1, this is going to be T2, and then so we're just going to assume they're different from the beginning, So if that's the case, now we just need to do the sum of the moments, or sum of the torques, and we're going to be doing it about the point where everything's spinning from, and we'll call that point O, So O, try and always do that. So, but anyways, so really in the end, the distance from O to the rope is going to be R, So same thing for right here, it's just the radius of the pulley. So anyways, so if we have T1 right here, its a line of action is going to continue up, And then basically in the end, if we compute the moment produced by it, it's going to be spinning like this then. And then so it's going to want to spin in this way, and so if you curl your hand in that direction, it's going to be positive for T1. So it's going to be T1 times by R, and it's going to be positive. So T1 times by R, and it's positive. So now let's do the T2. So T2 is going to want to spin like this then, like that, like that, and like that. That's if we extend our line of action, of course, and then it's this is also R, so in the end, if you curl your hands in this direction, it's going to be into the page, so it's going to be negative in the end. So I'm going to get negative T2 times by R, and we're going to set that equal to I times by alpha. So this is going to be the moment of inertia of the pulley itself, and then alpha is the angular velocity of the pulley also. So if we consider the pulley as massless, and then m is going to equal 0, which in the end means that I is going to also equal 0, just because the definition of I is the sum of the, so I to n, how many individual pieces of mass you have. So it's going to be I to n, the summation of mi times by r I squared, So if m is 0, then so is I, And so if we consider this as 0 then, so then we have T1 times by r minus T2 times by r equals 0. Then we can add T2 times by r to the other side. So it's T1 times by R equals T2 times by R. R's cancel. And then you know that the tension is going to be the same no matter where, if you're going about a pulley and that pulley is considered massless. So for almost all your problems, the rope, as long as it's the same rope, and doesn't matter if it's going around a pulley or not, the tension is going to be the same. So just because you consider the mass of the rope negligible, and then you also consider the mass of the pulley as negligible as well. And so that's all I have to show for this video, and I'll see you in part 2 then.